the talk of Olivier Benoist today from École Normale Supérieure is going to talk about sum of squares in local fields. So,
thank you very much for the invitation and for the opportunity to give a talk in this beautiful seminar. Indeed, I'm going to talk about sums of squares in local fields. And I'm going to start by recalling the history of the subject, and that is by recalling Hilbert's 17th problem. The question I will want to consider is the following. You fix a polynomial p with real coefficients in n variables, and you assume that it is a positive semi-definite in the sense that it only takes non-negative values on Rn. And you want to explain the positivity of P, and one way to do it is to write it as a sum of squares. So you ask the question, is P a sum of squares of polynomials? And this question is too naive. The answer is no, as was discovered by Hilbert himself in 1888. And you can actually give very simple examples. So the concrete examples were found much later, so around 1965. And an example of a polynomial that is positive but cannot be written as a sum of squares is the following one. Okay. And so Hilbert discovered these counterexamples, but he formulated also a better question, and that is, oh, sorry. His 17th problem. The better question is to wonder whether the polynomial P is a sum of squares, not of polynomials, but of rational functions. And this is a better question because it is now a question about quadratic forms in fields and not in rings, and they are much better behaved. And so much better behaved that the answer is positive. And this is the work of Artin. Okay, so in this talk, I will consider quantitative variants of this question that I'm now going to recall. There are quantitative variants. What do I mean by that? Well, now that we know that our positive polynomial is a sum of squares of rational functions, we may ask how many squares do we need? And to state theorems, I will start by giving two definitions. So I consider a field K, and I defined the Pythagoras number of K, P of K, to be the smallest integer, or plus infinity, such that all sums of squares in the field K are actually sums of P squares. So it is an invariant of the field K that really measures how many squares do you need to represent positive elements as sum of squares. And the Pythagoras number is usually considered together with another invariant that is important and that I will need to consider in my talk. That is the level of the field. So I introduce it now. So the level S of K of the field K, it is the smallest integer S, or maybe plus infinity, such that now -1 is the sum of S squares in the field K. And the first important results on these two invariants were obtained by Pfister around 65. And so I will state several results of Pfister. The first is that when you consider the field of real rational functions, the field that we considered above, its Pythagoras number is at most 2 to the n. So you see, when you combine it with Artin's positive answer to Hilbert's 17th problem, you deduce that a positive polynomial is not only a sum of squares of rational functions, but actually a sum of 2 to the n squares of rational functions, where n is the number of variables. So it really is, this statement of Pfister really is a quantitative version of Hilbert's 17th problem. The second theorem of Pfister that I want to state concerns the level of an arbitrary field now. So there are two parts. So the level may be infinite. That is, if -1 is not a sum of squares. And we know exactly, Pfister tells us exactly when this happens. It happens exactly if the field K is what we call real, that is, may be ordered as a field, admits a field ordering. And otherwise, it is finite. And the second theorem of Pfister is that when it is finite, it is actually a power of 2. Okay, and having said that, I can now concentrate again on fields of real rational functions. So, of course, now the field of real rational functions is a real field, so the level is infinite, but it is interesting to consider finite extensions of this field. And so if I take a finite extension that is not real, that is, whose level is finite, then the level is actually at most 2 to the n. Okay. So those are some of the main results proven by Pfister on Pythagoras number and level of fields of real rational functions. Okay, so I would just want to make a remark here. Pfister obtains upper bounds, and it is up to today unknown if these bounds are optimal or not. So it is unknown in at least 3 variables. So the topic of this talk is the study of local variants of this theorem of Pfister. And I will state the main theorem right now. It will be theorem 1. there are two parts. One part concerns the Pythagoras number, and it is the statement that the Pythagoras number of the field of real Laurent series in n variables is at most not 2 to the n, but better 2 to the n minus 1. Of course, if n is at least 1. So there is the exponent is better if you look at the local situation of Laurent series rather than the global situation of rational functions. And so it is a local analog of Pfister's first theorem, if you want. And the second theorem concerns the level. And again, you take a finite extension of the field of real Laurent series in n variables. And you assume that it cannot be ordered, that it is non-real. So in particular, the level is finite, and you can bound it again by 2 to the n minus 1. Okay, so this is the goal of the talk. So here are a few remarks. The first remark is that the statement concerning the Pythagoras number was a conjecture of Choi, Lam and Reznick. Oh, sorry. 1982, I think. And of course, some particular cases of this statement were already known. So first, Choi, Lam and Reznick themselves had proven the statement on the Pythagoras number in at most 2 variables. And Yong-Hu recently in 2015 had made further progress and had proven so the statement on the Pythagoras number for n is equal to 3 and the statement on the level in 2 variables. And the goal of the talk is to extend it to an arbitrary number of variables. A last comment that I want to make is that exactly as in the statement of, as in Pfister's theorems, these are only upper bounds and it is not known if they are optimal. So as in Pfister's theorems, it is unknown if the bounds are optimal in at least 4 variables, it is unknown. So in fact, this is not a different question. It turns out that the fact that Pfister's bound is optimal, that is this equality, is equivalent to the fact that the bound I obtain in the theorem is optimal. Okay, so I have stated theorem 1.
To the n minus 1, I guess. Anyway, sorry.
No, yes, thank you very much. Thank you very much. Thank you. So I have stated theorem 1 really for real Laurent series, but actually the proof yields a more general theorem and I will now state the more general and more natural theorem that is obtained in the proof. More generally, the proof gives. So I will state it as theorem 2. Okay, so I take A, an integral Henselian excellent local ring of dimension at least 1. Okay, with a residue field that I denote by little k. Now, okay, I assume that the characteristic of k is 0, because otherwise these questions are not very interesting anyway. And I need to control the cohomological dimension at 2 of the field k where I adjoin square root of -1. That is the virtual cohomological dimension at 2 of k. I denote it by delta. And then there are 2 statements. One statement on Pythagoras number. So if A is regular and the residue field is a real field that is maybe ordered, then the Pythagoras number of the fraction field of A is at most 2 to the n plus delta minus 1. Okay. And there is a statement on the level. And there I can look at the level not only of the fraction field of A, but also on function fields over this fraction field. So if K over frac A has transcendence degree M and is not real, since it is not real, the level is finite and I can bound it. By the following power of 2. And again, there is this -1 that improves the bound. Okay. And that theorem 2 implies theorem 1 is immediate. You just take A to be the ring of power series. And just an example of an application of theorem 2 is the fact that this field has Pythagoras number at most 2 to the n plus 1. And it is an open question. It is unclear. It may be asked. And it has been asked by Yong-Hu, for instance. If you may improve it. Okay. Are there questions at this point? So if not, my plan now is to explain the proof of the theorem, actually of theorem 1, that is really, this contains already all the significant difficulties in the proof. So I will explain how to prove theorem 1. And the proof.
Can I ask you a question? So
yes,
in this last one, what is the bound? What is the constraint on n? The very bottom.
Sorry.
Can
you repeat?
Question you said, do we have less than or equal to 2 to the n?
Yes.
This is definitely not true for n equal 1, right?
Okay. Thank you very much. Thank you very much. It's for n at least 2. You're right. In fact, when you look at rational functions over Q, the Pythagoras number is lower than expected as soon as there are at least two variables. And this is a deep and difficult theorem of Janssen. So you may ask if the same, I say two, maybe I want three, I don't know. You're totally right. You need enough variables. Thank you very much for pointing it out. I really want at least three variables. Thank you very much.
Could you say what this theorem of Janssen is? I didn't quite catch that.
Okay, I didn't say it. Okay, so this question here would be local analog of a theorem that is due to Janssen, and that tells you that the Pythagoras number of this field is at most 2 to the n plus 1 if n is at least 2. So what my theorem tells is that you improve the exponent by 1 in the local situation. What Janssen tells you is that you improve the exponent by 1 in the arithmetic situation, and you can ask in the local arithmetic situation, can you improve the exponent by 2? This is the content of the question here. Okay. So let me so the proof relies on cohomological tools, and more precisely on the following proposition. I call it a proposition, but it is a it is a consequence of the Milnor conjecture proven by Voevodsky. So I mean, it is a deep theorem actually, and it says the following: you take a field of characteristic not 2, you fix a non-zero element and an integer, and I claim that the following are equivalent. So assertion 1 is that the element A is a sum of 2 to the r squares, I mean, in the field K. And assertion 2 is a cohomological reformulation of this statement. It is the following: you take the class of -1, you raise it to the power r, you multiply it with the class of A, and it is the assertion that this vanishes in H r plus 1 of K z mod 2. And so here, the class of X, this is the class of an invertible element in K star mod the squares that I view as the H1 of the field K with z mod 2 coefficients. And I take powers here in Galois cohomology. Okay, and okay, and I will use this proposition as a black box. I don't think I will explain anything about it. Really, what the Milnor conjecture does is relate quadratic forms over the field K with Galois cohomology, and the direct consequence of this link between quadratic forms and Galois cohomology is this equivalence. It is a concrete application of the Milnor conjectures. And the proof of the main theorem has 2 steps. First, you show that the above proposition, that is the Milnor conjecture, implies the assertion on the level. So, and second, you use again the Milnor conjecture plus the assertion on the level, and you deduce the assertion on the Pythagoras number. And so you, even if you're only interested in proving the result about the Pythagoras number, you need to prove the result on the level first, and it will be clear how this enters the proof. So, and I will do these two steps one after the other, and I will actually start by explaining how to deduce from the statement on the level the statement on the Pythagoras number. So it's really the proof of that the statement on the level implies the statement on the Pythagoras number. Okay, so let me do this. I take an element that I call A, an invertible element in the field of Laurent series in n variables. So I call this field K, and I assume that it is a sum of squares. What is my goal? It is to show that it is a sum of few squares. Actually 2 to the n minus 1 squares. And in view of the above proposition, in view of the Milnor conjectures, that the following cohomology class vanishes. So I call the class alpha. Okay. So I will want to argue. I will argue geometrically. So I will work. On the scheme, the local scheme, that is the spectrum of the field of power series. And I view A, for instance, as a rational function on this scheme. Now, I want to show that alpha vanishes. So alpha is a class in the cohomology of the fraction field of S. But to show that the cohomology class vanishes in such a fraction field, the first thing to do is to verify that it has no residues. If you want to show that the cohomology class vanishes, it better have 0 residues. So the first step really is to show that it is unramified, that its residues vanish. And this is what I do. I will compute its residue at a codimension 1 point. So I take inside of S, I take an integral divisor, so a codimension 1 subvariety. And I call its generic point eta d. And I look at the residue along D of the class alpha. It is a class that lives in cohomological degree n minus 1 of the field eta d with z mod 2 coefficients. And in view of the very concrete definition of alpha that we have, we can compute this residue. There is a formula. It is really equal to E times minus 1 to the n minus 1. And what is E? E is the order of vanishing of the function A along the divisor D. Okay. And now I want to show that this residue vanishes. There are two cases to look at. The first one is the case where E is even. Well, then E is 0 mod 2 and the residue is 0. So easy case. And the second case is when E is odd. Now, the thing to notice is that the field eta d, the residue field of eta d, is not real. So let me write kappa of eta d for the residue field. So let me justify why here between brackets. The reason is that a sum of squares in a field, say in this field, where kappa is a real field, has even t-adic valuation. So it is a very easy lemma to prove. It is really a manifestation of the fact that a positive polynomial cannot have a root of even order, sorry, of odd order. A positive polynomial only has roots of even order. And here, how do you apply it? Well, the element A is a sum of squares. So if the residue field of eta d were real, then its order of vanishing would have to be even. But here I have assumed it is odd. Okay. Okay. So now the residue field at this point of codimension 1 is a non-real field. But it is a non-real field of the kind we consider. That is, it is isomorphic. It may be realized as a finite extension of a field of a Laurent series in one variable less, just because it has D is a codimension 1 subscheme. So I can apply to this field the statement on the level. By the statement on the level, this field has level at most, okay, 2 to the n minus 2. That is, in this field, minus 1 is the sum of at most 2 to the n minus 2 squares. But this information on the level, I can translate it cohomologically thanks to the Milnor conjectures, thanks to the proposition that I have recalled above. So really, by the proposition, by the Milnor conjecture, this is equivalent to the vanishing of this class. Okay. And I win in view of the formula for the residue vanishes. Okay, so this was the first part of the proof. You had this cohomology class you wanted to kill. The first thing to do was to show that it was unramified, that it had no residue. And now what do you need to do? Now you have a class alpha that is unramified on the scheme S that has no residue. And now you need not to kill not a cohomology class in the function field, but an unramified cohomology class. But in our setting, we know a lot about unramified cohomology classes because our scheme S is a local regular scheme. So since S is local regular, we can appeal to the so-called Gersten's conjecture. So that is due. So I need to quote Bloch and August, but the statement in the required generality is due to Panin. What does this Gersten conjecture tells me? Well, alpha, as any unramified cohomology class, leads to an actual cohomology class of S. So a class I will call alpha tilde in Hn of S Z mod 2. Okay. Okay, and there is a little bit of work to still to conclude, but we are very close. What do we gain? Well, this group Hn of SZ mod 2, now it is actually a very small group. It is the cohomology of a complete local ring, and by proper base change, it is the same as the cohomology of the residue field. So, I'm sorry. Here by proper base change, it is the same as the cohomology of the residue field, that is the field of real numbers. And well, the cohomology of the field of real numbers is not very complicated. In every degree, it is Z mod 2. And in every degree, it is generated by a power of the class of -1. So my class alpha tilde, it is either 0, which I want to show, or this other class that is -1 to the n. And I just need to show that it is not the class -1 to the n. And to check whether it is 0 or the class -1 to the n, I do the following trick. I send alpha tilde to the cohomology of a real closed extension of S. Any. You choose one, any real closed extension of S. And for the same reason as for the field of real numbers, this cohomology group is very simple. It is Z mod 2 generated by the class of -1 to the n. Okay, and okay, and now a very simple computation concludes. I look at the image of alpha tilde in R, so it is exactly the same as the restriction of alpha to R. But alpha, it was defined by a very simple formula that is here. It is -1 to the n-1 times A. And remember that A is a sum of squares. So here, this is -1 to the n times A. But since A is a sum of squares, in this real closed field R, it is a positive element. It is itself a square. So the class of A, it is the class of 1. Sorry, it's n-1. And the class of 1 is 0. So here I have used again that A is a sum of squares. Okay. And this shows you that alpha tilde cannot be the class of -1 to the n because it vanishes in the cohomology of my real closed field. So it has to be the trivial class. Okay.
So can we think of R as being obtained from S by adjoining the square root of A?
Yes, of course, when you go from S to R, absolutely, you will in particular add the square root of A. Yes, absolutely, totally. Yes. Yes, absolutely, because A is a sum of squares. Okay, so this shows that alpha tilde is not the non-trivial class, but there are only two classes. So it is 0. And this completes the proof. Okay, so the general idea of the proof is very easy. You need to kill a cohomology class. You first kill its residues. And to do so, you need an information, which is the theorem on the level, which remains to be proven. And once it is unramified, there are many theorems on unramified cohomology. And here it is Gersten's conjecture that is useful. Are there questions? Okay, so if there are no questions, I will now explain how to prove the theorem on the level. So it is the last paragraph. So maybe I recall the statement. So you take K, a finite extension of this field of Laurent series. And you assume it is non-real, that is that it cannot be ordered. And you want to show that the level is at most 2 to the n minus 1. Here, n is at least 1. And as before, what is our goal? Well, to show that the level is at most 2 to the n minus 1, that is to show that minus 1 is a sum of 2 to the n minus 1 squares. But by the Milnor conjectures, by the proposition I have recalled before, this is a cohomological statement. This can be reformulated as follows. So by the proposition, need to show that the class minus 1 to the n, which belongs to the nth cohomology group of K with Zimmer-2 coefficients, vanishes. And this class, okay, I call it again alpha, and I want to kill it. Okay, as before, I will want to argue geometrically. So I will introduce the schemes on which my cohomology classes will live. So to argue geometrically, what do you do? So you denote by A the integral closure of the ring of power series in K, and you denote by S its spectrum. And the difficulty now is that this, so it's a finite ring extension of the ring of power series, but it may be badly singular. And so to argue geometrically, I will choose a resolution of singularities of it. And I choose a resolution of singularities in such a way that the special fiber, okay, so the closed point of my local scheme I call little s, and the special fiber I will call it E. So it's x little s. And I assume in my resolution of singularities that the special fiber is a normal crossing divisor, a strict normal crossing divisor in X. So the picture, okay, I will try to draw a picture. S is my local scheme. It is badly singular at some point, little s. And I take a resolution of singularities, x of s. That will maybe, I don't know, look like that. And inside of x, I have the inverse image the inverse image of the closed point of the special point of S. Okay. And X is X has no singularities. And so remember that we want to kill the class alpha, that is a cohomology class in the of the function field of X. And you might think, okay, first I'm going to prove that it is unramified, but here it is obvious that it is unramified. Actually, it is defined as its definition shows that it is a cohomology class of X, because the class of -1 is well defined in the cohomology of any scheme of characteristic node 2. So one can consider alpha really in the cohomology of the whole scheme X. Again, as the nth power of the class of -1 that is well defined in the H1 of X. It is the image of -1 by the boundary of the Kummer exact sequence. And here, yeah, I mean, as before, it's always étale cohomology. And we want to show that alpha vanishes in the cohomology of the function field of X. And it is the same as to say that it vanishes in the cohomology of some open subset of X, that it vanishes after removing some closed subset of the scheme X. And now the trick, it looks difficult because you do not know what closed subset to remove so as to kill the class. And the trick here is that there is a way to choose a closed subset that works. There is a choice that works that you can make now. And okay, so we need to find D in X closed subset such that alpha restricted to to X minus D vanishes, well, in the cohomology of X minus D with Z mod 2 coefficients. Indeed, then alpha restricted to K is equal to 0. And I claim that we can choose D as follows. Well, you look at X over S, it is a resolution of singularities, so it is a projective morphism, and you can embed X in some relative projective space over S. And now I just take a hyperplane section of X. So let D be a general hyperplane section of X in an embedding.
Olivier,
I
what
take
means
it.
general?
So
what means general over S? Over field, I know, but over S.
So general, the only things I need are the following. So in the sense that inside of X, the union of D and of the special fiber is again a strict normal crossing divisors in X.
Okay, merci.
And this can be achieved. This can be achieved really if you choose it generally enough. Okay, and so this is what I claim, and now I need to prove it. Okay. So what is the situation? I have my class alpha in the cohomology of the scheme X, and my goal is to show that it vanishes in the complement of the subscheme D that I have just constructed. Okay, now the cohomology of X, it is actually, I mean, I don't know, very simple, but you can actually compute it by proper base change. So really by proper base change, the cohomology of X is isomorphic by restriction to the cohomology of the special fiber. And I complete the diagram. Here I have the cohomology of the complement in the special fiber of the divisor I constructed. Okay, and I want to conclude from this diagram that alpha vanishes in the cohomology of X minus D. And there are two, to do so, you need to know two things. The first is that this group vanishes. And this is, I call lemma 1. And the second thing you need to know is that this map is actually also an isomorphism. And this I call lemma 2. Okay. And this lemma 1 and 2 conclude. Okay. So in these two lemmas, lemma 1 is standard and lemma 2 is less standard, but I will start by lemma 1 because it is much easier. Lemma, so you call this U, and lemma 1 tells you that if you take a variety U over R that is affine with no real points and has dimension D, sorry. Well, then the cohomology of U, the étale cohomology of U with Z mod 2 coefficient vanishes in degree bigger than the dimension. Okay, and of course, if U is not, so the hypotheses are satisfied here. So U is affine because it is the complement of an ample divisor, and it has no real points. This is a consequence of the hypothesis that the field K is non-real. That the field K you consider is non-real implies that the special fiber has no real points. And okay, and over the complex numbers, this theorem is standard. You can prove it by comparing to Betti cohomology, and the same proof works over the real numbers. So really the étale cohomology of U with Z mod 2 coefficients. It is isomorphic to the Betti cohomology of the complex points of U with Z mod 2 coefficients. So this is not true as written, but it is true if you take equivariant cohomology with respect to the action of complex conjugation. But now, since there are no real points, complex conjugation acts fixed point free. So this is nothing but the cohomology of the complex points modulo action of complex conjugation. And okay, and now this space, since U is an affine variety, this space, it has the homotopy type of a CW complex of dimension well D. So its cohomology vanishes in higher degree. Okay, and it's really an incarnation of the Weak-Lefschetz theorem, if you want. Okay, now to lemma 2. Okay, I don't know. So this should be really, this really is a variant of theorem of Saito and Sato. And I am really indebted to them for having devised their theorem. So they applied their theorem over a base that is, say, the p-adic integers. And here I adapt it to a base that is the field of the ring of Laurent series over the reals, for instance. But it really is the same theorem and the same proof. And so, okay, the theorem says that, well, okay, it's this isomorphism, and it is really incredible because you see, it is the statement that you would expect from the proper base change theorem if x minus d were proper. But x minus d is not proper because I have removed the closed subset. So it is a proper base change theorem it's a base change theorem in a non-proper situation. Okay, so maybe I run that. This is a proper the base change theorem. And the proof, okay, so I'm not going to tell anything about the proof because I do not have the time, but the proof uses in a very important way the fact that D and E, they're both simple normal crossing divisors that intersect transversally so it uses in a very important way the geometry of simple normal crossing divisors. So the statement is not as general, of course, as the proper base change theorem. You really need here that all the subscheme that appears, all the subschemes that appear are simple normal crossing divisors, all intersecting transversally. Okay. And
is it right that this has sort of nothing to do with the real numbers?
It has absolutely nothing to do with the real numbers, nothing to do with the p-adic integers either. It's a statement that you can write above any Henselian local, excellent local ring. It's a statement in a local Henselian setting. Okay, and I will stop here.
Okay, so maybe question or comments. So please be free to use the chat.
I guess one might ask, you mentioned that there's an equivalence between your statement being optimal about function fields and the statement about Laurent series fields. So why is that equivalent?
Can you repeat? I'm sorry, I didn't understand.
Sorry, you had a question about, you said that it's equivalent whether the statement for function fields is optimal or for local fields.
Yeah,
so
the reason, and that also explains why there is an exponent n-1 in the Laurent series field case, is what is the n-1? When you're in the, maybe I should go back to my picture here of X. If S is n-dimensional, X, which is a resolution of singularities, is also n-dimensional. But because of the proper base change theorem, what is important is not X itself, but the special fiber. And the special fiber is made of n-1 dimensional varieties. And so the components of the special fiber, they will have typically, their function field will have cohomological dimension n-1 virtual, and not n. And really, if you have an example where Pfister is optimal, say a variety X over the reals of dimension n, whose function field has level 2 to the n, what are you going to do? You're going to arrange a picture X to S like in the, where where the real variety appears as a component of the special fiber. So the link between yes, if you want to compare Pfister's results and the results over Laurent series field, really, real varieties of dimension n-1 appears as component of the special fiber of such resolution of singularities, when X here, as in the picture, has dimension n. Does it answer the question?
Yeah, thanks.
Okay. Well,
So in this picture, is little s the closed point?
Yes, exactly. Yes. So yes. So in the setting I was in, it was really the reals, and so E, which is a scheme over S, is really just a variety over the reals, a singular one.
So if it happens to be smooth, then I guess you don't need anything else. Right.
You mean to compare the optimality in Pfister theorem and oh.
So how does the argument simplify if big S is smooth?
Actually, it will not simplify a lot. I think you cannot get rid of Saito-Sato, for instance, because you will still want, if the special fiber is smooth, you will still want to remove a closed subset to kill your cohomology class. So you will still want to remove a D, and you will need to write exactly the same diagram here, and you will still want to have an isomorphism in the bottom line, and it will be still hard because it will be a base change theorem in a non-proper setting. And I don't see that. So maybe it would be a particular case of Saito-Sato that is maybe easier to prove, but you will still need to use the ideas of Saito and Sato.
So you would have to blow it up then, and E would be the exceptional divisor for that blow up.
Yes. But I do not think it leads to a big simplification of the proof, since the hardest part of the proof is to use Saito-Sato.
But in Saito-Sato, the basic ring was a DVR, wasn't it? Dimension 1.
Yes, the base ring, but
here
it doesn't.
You want something of high dimension.
Yes, but the fact that the base is one-dimensional doesn't play any role in their proof, actually. There is absolutely nothing in their proof that uses that the base has dimension 1. It uses only that the base is Henselian. So it applies in our setting with no modification to the proof.
Yeah. Other questions, comments?
Well, I have a trivial obvious question, and in a talk like this is, does this work on any real closed field?
Oh, yeah, yes, it does.
The only place where I saw something is when you started talking about CW complexes, but apart from that.
Yes, okay. Okay. It's of course it's not useful because the cohomology of varieties of a real closed field has been studied in detail by many people. For instance, Scheiderer, and he knows this kind of vanishing very well. And so the theory is fully developed, and it is fully developed. It is fully developed to the extent that actually the residue field can be any field. Just the virtual cohomological dimension of the residue field is going to appear.
Yeah.
Okay. One last question, maybe?
There's a question in the chat.
Ah, okay.
If we define the analog of Pythagoras number for primes other than 2, can the argument be just to a... Okay, so you're asking for sums of pth powers for other values of for nth power for other values of n. So I think that these kind of questions are very interesting if n is even, and they've been studied, and I do not know the I do not know this question well enough to answer. I'm sorry about that. Sums of 2nth power have been studied extensively, and I do not know the results. Sums of squares are particularly interesting because in a field, sums of squares are exactly the positive elements. But there are also a lot to say on sums of 2nth powers, and I'm sorry I can't answer.
Okay, so thank you very much for
Actually, I can tell you something about sum of nth powers. There's a criterion by Eberhard Becker that tells you when an element is a sum of nth powers, when n is even. And so the criterion is very simple. It's a beautiful criterion. It's very simple. It says, so n is even, and say you have a field of characteristics 0. An element is a sum of nth powers, if and if it's a sum of squares, and if and only if for any cruel valuation with formally real residue field, the valuation is divisible by n.
Okay, thank you.
Okay, so I think that's the right moment to end the talk. So thanks again, Olivier. And let me just announce that next week the seminar will welcome Vladimir Popov. Okay, so see you next week then.